So we are going to look at what happens when we take all of the works that we have available to us and we put them together with the energies as well. So we can talk about this work as being if I add up all the works, it will tell me about the change in kinetic energy. This is the work-kinetic energy theorem. So we're going to expand this a bit and see how we can use it to solve problems. So if I add up all the possible works, so there's an input work. This would be done by some applied force. There's also work done by friction, so if there's friction involved. There could be work done by gravity in the problem. There could also be work done by a spring, which I'm just going to call an elastic object. So if I add up all those works, I'm going to equal a change in kinetic energy. Now, rather than talk about work done by gravity and work done by elastic, because they're conservative forces, I can talk about them as negative changes in potential energy. So I'll make that substitution here and say that the work done by gravity is the negative change in gravitational potential energy, and the work done by the spring is the negative change in elastic potential energy. Now I'm going to go ahead and, since they're negative, I'm going to move them over to the other side of the equation here to make them positive. So I'm left with work in plus work done by friction equals a change in kinetic energy plus a change in gravitational potential energy plus a change in elastic potential energy. And so what I have now in my equation is, on this side I have non-conservative forces. On this side I have my group of mechanical energies. So this is going to be kind of the basis for my equation. I'm going to take it one step further, and then we're going to see what we do with it. We're going to expand these deltas, which mean final minus initial. So moving over here. All right, so this is my expanded version. So I have K2 minus K1 and UG2 minus UG1. So the 1s and 2s here stand for a starting point and an ending point. So I'm always going to need a start point, which I'll call point 1, and I'll need an end point, which I'll call point 2. Okay? The other condition I need to have here when I set up this problem is I need to choose where is my reference height. Where is height equals 0? Okay? So once I've made these three choices, now I can start to kind of reduce my equation into something a little more usable. So I would cross out work in if there was no applied force. I would cross out work done by friction if there was no friction. So you're basically asking yourself a set of questions as you start to set up this equation. Is there an applied force? Is there friction? Okay. I would cross out K1 and K2 if the velocity, or the speed, I should say, is equal to 0 at that point. Okay, so if it was not moving at point 1, I would cross out K1. Over here, I cross it out if the height equals 0. Okay? Ideally, when I make this choice of where the height equals 0, I want to choose it at the lower of my 2 points, so at least one of them crosses out for me. And then over here, these cross out if either there's no spring, or the spring I do have is not compressed or stretched. And all of this is coming from essentially the equations that support these. So for instance, kinetic energy is 1/2 mv squared. So if v is 0, k is 0. Ug is mgh. So if h is 0, ug is 0. And then UEL is 1/2 kx squared. So if there's no spring constant, there's no spring, it's 0. Or if it's not stretched or compressed, it's also 0.